Hello everyone. Today we will be discussing fluid property tables. Whenever you're analyzing a fluid, whether in fluid mechanics, thermodynamics, etc., you need to know the properties of that fluid. These properties include internal energy, pressure, temperature, specific volume, etc. So how do you determine these properties? Well, there's two ways. One is by using a differential equation, but that equation will not be covered in this series because it is very, very rarely used. Your professor might touch on it, and you might use it for that class, but you're not going to use it in industry. In industry, you have these engineering tables. Now, these tables have been created over the centuries to detail specific properties of fluids at a given pressure and temperature. For this lesson, we shall be using one of the most common fluids, which is water. So as you can see with these three tables, Table 1 dictates saturated liquid, saturated vapor properties. So, well, if it's between saturated liquid and saturated vapor, we must be inside the dome. So here we have 1. Table 2 details the properties of a compressed liquid. Now if you recall, compressed liquid is before the dome, so we are over here at 2. Superheated water vapor, table 3, is when you're past the dome and you're completely vapor. So we shall be over here, past the dome, labeled 3. For the first part of our lesson, we shall cover table 1, when you're saturated liquid and saturated vapor. So let's say my water is at 60 degrees Celsius and I'm saturated liquid. Well, that means I'm right here, and this temperature line is 60 degrees Celsius. Well, if I'm right here, I can go to the table for saturated liquid, because this is the saturated liquid part of the graph, saturated vapor, and I know my pressure, which must be 0.1994 bar. I know my saturated liquid, which is 1.02 times 10 to the negative 3. Here at the saturated liquid, you're going to have VF times 10 to the third. That just means it is 1,000th of what this value states. So like I said, if my temperature is 60 degrees Celsius, my specific volume at saturated liquid is 1.0172 times 10 to the negative 3 meters cubed per kilogram. Now, I also know my internal energy of the fluid, I know my enthalpy, and I know my entropy. So, what if I'm a saturated vapor? Well, I know those properties too, because I have a saturated vapor value. So if I'm at 60 degrees Celsius, here's my saturated vapor, or a specific volume for my saturated vapor. Here's my specific internal energy for saturated vapor, specific enthalpy for saturated vapor, specific entropy for saturated vapor. Now, you may notice this value here in the enthalpy chart. This is used for when you are dealing with a specific spot inside the dome. If you recall from our previous lesson, in quality, we'll do enthalpy because that's that specific part. Enthalpy of our fluid is HF plus our quality times the difference of our saturated vapor enthalpy and our saturated liquid enthalpy. What this HFG is this. This is HFG. So you can write it as H is equal to enthalpy of saturated liquid plus X times HFG. Where I got this from, you have this value here. If you don't have this value, you simply subtract these two, and if you pause the video and do that subtraction, you will get the value I circled. So let's say I'm at 60 degrees Celsius and I want to increase the pressure. Well, if I'm increasing the pressure, I'm going to stay on this line, I'm going this way. You'll see that I am in the compressed liquid region. Well, that means I'm completely liquid. So you will go up to table 2 and you'll get your property. Now, table 2 does not have 60 degrees on here, so you'd have to do interpolation, which we will cover later on in this episode. Now, let's say I want to decrease the pressure of my fluid. Well, remember, when you're inside the dome, you're isobaric, and so now I'm decreasing my pressure. Well, if I'm decreasing my pressure, I'm now in my superheated vapor region, so I'd go up here to table 2, and I'd pull a value from this table depending on my pressure, because you can see in our superheated vapor table, we have a given pressure here, which is 0.06 bar. We are given its saturated temperature, means when it is changing from liquid to gas, and we have the properties at a given temperature and a given pressure. So remember, when we're outside the dome, we need a temperature, pressure, or any other two independent properties. So now here's the thing. You should notice that even though this says superheated vapor, that does not mean the fluid is very, very hot, because 60 degrees will not, well, it might burn your skin slightly, but it won't hurt you, really. This superheated simply means it has just completed the transition from
Hello
vapor
everyone.
to
You will have
gas.
noticed what I just said was
So,
converting it from vapor to gas. I
yeah,
meant
that's
to
superheated
say
vapor.
converting liquid to
So,
vapor.
but what happens if you need a specific temperature? Like, hey, I'll use superheated vapor. I'm at 100 and I'm at 100 degrees Celsius. My pressure is 0.06 bar. What are my values? Well, you would use what's called linear interpolation, which I shall label here, assuming my mouse reconnects. Linear interpolation. So here I want to determine my, let's say I want to determine my specific volume at when my pressure is 0.6 bar and my temperature is, let's say 90 degrees. All right, so I'll let you get those values here. You can pause the video to grab those values, but I have the table up here on another screen, so I shall show you. So if my temperature that I want is equal to 90 degrees Celsius, my pressure is equal to 0.06 bar, what is my specific volume? Well, at 0.06 bar, if you look at the table, you will see that it is going to be superheated vapor. I shall copy this table for you. I shall not copy this table for you because my computer is not wanting to cooperate. There we go. Sorry, my mouse disconnected. Here we go. Here's the table. So, 90 degrees, 0.06 bar. As you can see, at 0.06 bar, 90 degrees is superheated vapor. I'm past the saturated temperature. Well, there's no values for 90. How do I determine this? Well, I know the values for 80. I know the values for 120. So I can use those and create a line. So if I know on a PV scale, here, no, that's a bad axis. That's a bad graph. I'm not a good drawer. PV diagram, or PT diagram. No, that'd be a TV diagram. TV. So I have here a specific volume. Here, this is 30.219, 120, and this is here 27.132 at 80 degrees. I can draw a line here, and I can be like, okay, what is that value? That is linear interpolation, simply creating a point, creating a line, finding your point on that line. So, for this example, we shall use this equation. you have T1 is equal to 80 degrees Celsius. My specific volume is 27.132 meters cubed per kilogram. For T2, I am at 120 degrees Celsius, and my specific volume is 30.219 meters cubed per kilogram. So I'm going to do T1 minus T2 over V1 minus V2 is equal to T1 minus T over V1 minus V. Now, it does not matter if you do T2 minus T1 and then T2 minus T. The equations are the same. The point is you need to create this line and find the point on that line. Or you can do this. You know the slope between these 2 points here must be the same as the slope between these 2 points here, the 120 and the 80. So if I find the slope between the 80 and the 120, that must equal the slope between my 80 and the 90. That is what this equation here does. So let's plug in our values, see what we get. Well, we're going to get 80 minus 120 over 27.132 minus 30.219 is equal to 80 minus 90 over 27.132 minus V. Well, the left simplifies out to 12.95. 12.95 is equal to negative 10 over 27 minus 132 minus V. So I need to solve for V. Isolate it. 32 minus V is equal to negative 10 over 12.95, which is equal to negative 0.77175. So I get 27.132 minus a negative 0.77175 equals V. Solve that, I get 27.132 minus that. I get 27.90 is equal to V. So when my temperature is 90 degrees Celsius, my pressure is 0.06 bar. My specific volume is 27.90 meters cubed per kilogram. That is linear interpolation. Now this can get messy. For example, what if you had to find 90 degrees Celsius at 0.2 bar? Well, that's not on this table. So you'd have to do an interpolation for 80 degrees Celsius at 0.2 bar using this exact same method. So instead you'd have 80 at 0.06 bar, or you'd have 0.06 bar, your specific volume at 80 degrees, your specific volume at 0.35 bar, and you have to find now your specific volume at 0.2 bar. Rinse and repeat for when you're 120 degrees Celsius, and then do this process again a third time to find your temperature at 90 degrees, 0.2 bar, that'd be your specific volume. So this just gets messy, but it follows the exact same process. As always, thank you for joining me. If you have any questions, I will be happy to reply in the comments, or I can make another video and answering those questions if one question repeatedly comes up. Thank you for joining me. Have a nice night.